Hello everyone, welcome you all to the first lesson of assembly language. So this lesson covers the basic of assembly language as well as level by level as we go up. So you'll see the expert level assembly language as well. So let's start with the basic first. So the first question when you hear about basic assembly language comes up is, what is assembly language? Because like the code that you see, the C code that you write, is it that C code that the computer can interpret? It's a no, right? So the computer deals with binaries, only 0 and 1. So that's the two thing, just a 1 or a 0 that the computer will understand. But to convert your data that you write in a C code or in a C++, Java, Python, whichever language you use, so the code you write that has to convert to the binaries, right? So if they get converted to the binaries, so there is a specific path that it has to be taken to. So in the intermediary part, there comes the assembly language. So it's a low level language which only communicates with the processor directly. So what this is like for now, we'll be covering only the Linux 32-bit assembly. So similarly, you'll have the 64-bit assembly as well. That will have more number of registers, much more details will be there. So like we'll be covering the 64-bit memory as well in the later lessons as well. So the Intel and ARM. So there are two, what do I say? There are two processors. So like the Intel flavor, the instruction, the assembly language instruction that are written for Intel processor as well as that are written for ARM processor are like far away, like pretty different. So like if you, but the basic is still the same. So like if you understand the basic of assembly language, you can apply the same concept whether the processor is a Intel or it's a ARM. So like for both the processors, your basic will be same. So let's move forward. So this is how the actual your C code gets converted to the machine language. So this is where you are having the C code. So this is your C program, the C hello.c. This is where you write hello.c. This is your hello.c, hello.cpp. So like this is C code, this is C++ code. Now when you pre-compressed code is in hello.i, then you get the compiled code which is hello.s or the object code, whatever you call it. So object code is hello.o. So you'll get a, like in C language you'll get a a.out file. So that a.out file is the executable part, this part. So in C++ you are getting this hello.exe. Similarly, if you are getting a.out, that is also the executable part, the executable file. So what happens is, like once you are having the object code, then the different modules are linked by the linker loader. That's a function of linker and loader to prepare your executable file. So you're having the executable file. So whether it's a Windows executable or Linux executable, based on the OS, that executable can run free, like on its own on that operating system. This like a, what do I say, a high level picture of the registers that are available. So what are registers? The thing is, like for bringing each and every value, you can't go to the memory, fetch it, and then you can use it. So that's not a actual process. That's very trivial process which will like too long. The time taking for that process will be too long. So there comes the new picture which is called the registers. So registers, but the limitation is like now, like many of you must be wondering, why don't we bring the entire data register and process it? Quite easy, man. We can do it. But the thing is, registers are limited. So we can't use as many registers as we want. So we are having in 32-bit register, we are having 32 registers. So if it's a 32-bit, so 32 register. So like you have to use the register as efficiently as possible. So there comes your compiler optimization as well. So the compiler tries to optimize your code so that it can fit the maximum. It can actually execute the code in the minimum time. So these are the, like 31 the 32 registers. And like these are all the popular registers, but like there are a hell lot of registers apart from these, like EAX, EBX, ECX, EDX, EBP. EBP is your base pointer. ESI, hey, yeah, I'm back. So ESI is your stack index, the source index pointer. Now EDI is the destination index. So what this means is like, that is the start, this is the end, that's it. ESP is your stack pointer. So what is the difference between EBP and ESP? EBP is the base pointer. It will point to the, like the starting point of the stack, the top variable that we use in C. And ESP is like the stack pointer. So that will always point to the top of the stack. The ESP will point to the top of the stack. EBP will point to the bottom of the stack. So it's at the B, it will be bottom, and it's a base pointer. So always it will be on the base, right? So it will be on the bottom of the stack. ESP will point to the top of the stack. What is EAX? So EAX, so majorly all the sys calls, the system calls that are occurring. So entire system calls happens to EAX. Whenever a function call happens, any value is returned, that value will be stored in EX. So this is like a overall use of the registers. I'm not saying like EX is only used for these two functionalities, but this is the majority of the cases where EX is used. EBX, ECX, EDX. So these are three registers which are used for like passing on the arguments. Majorly that are used for passing on the arguments for a function call. So apart from these registers, there are a hell lot of registers, as I already said. So like if you suddenly see some new register while like debugging your code, don't get like panicked. There can be more registers. So yeah, this is the whole scenario that I already explained to you. Yeah, so one thing like the EIP, I missed this register EIP. So this is the instruction pointer. So what this means is like this will point to the current instruction that is executed. This is the look at the memory model. So here you can see like there are different sections of assembly call. So this is all the section of assembly. This is the start section. So this is like if you write a hello world program, so there you will have a main function. So like this main function will be transformed to the start in the assembly language. So the start section will be the code that will execute at the first. The text section is a section which has the executable code. So this will only have the executable part. Anything that is there inside text is the executable part. The next section is the data section. So this is the section where we'll initialize our variable. So like if you want to initialize a is equal to 2, b is equal to 1, so that entire code will be there in the data part, in the data section. BSS section is the section which has the uninitialized data. So if you write any variable int a and you with a semicolon, so that means you're just initializing the value. You're not assigning a value to the variable. So those variable will be there in the BSS section. Now I guess you guys must be having a fair idea of the different sections of assembly language. So now we can quickly move on to the memory. So this is how the entire memory model looks. The first is your kernel space, then is the stack, and the major part. Stack grows downwards, right? Stack, right? So this is the way where stack will grow. Yes, stack will grow in this way. This is the shared libraries. So this will contain the all the shared library. Like if you import something, all those libraries will be there. This is a heap section. Then your BSS, the data, and last is the executable part. This is the executable part. This is the executable part of the code. Okay. Now you have GCC for C code. You have G++ compiler for C++ code. Now what do you have to compile a assembly language code? So there comes your NASM. So NASM is used for compiling your assembly language code. So how to install NASM? So these are the steps you have to install NASM. You have to install the libraries. That's it. NASM is there. So it will be better if I quickly jump on to our first assembly language code. So let's quickly move on to the practical section assembly language. So let me quickly fire up my virtual machine. So this Kali. Okay, so like this Sublime Text. You can use any text editor, but I used to prefer Sublime Text. That's my choice. If you want something else, you can. That's your choice, man. So what actually I'm wanting to, I don't know. Okay. So something is already written. Yeah. So you must be aware of these sections. The text section, start. This is your text section. So like now you're having the start. So this text section contains the entire code, that is the executable part. So first instead we'll move something on EX to something, okay? So we'll move EBX to something, we'll move ECX with something. So now let's see. So what this is like what assembly language does is like it actually correlates the kernel space with the user space. So I already showed you that memory mapping, right? So this is the kernel space, but a user only has access to this space, the user space. He doesn't have access to the kernel space. So if you want to have access to a kernel space, there is something called system calls. So you have to generate a system call which will, what do I say, which will actually convey your message to the kernel. So if I quickly go to the code that I was writing, so here, so what that is like, every system call, like a read, you're reading something, you're writing something, a copy operation, a paste operation, every operation has a system call. And what the interesting part is like every system call is mapped with a number. So like every operating system has a different number for a different system calls. So if I go to this directory, which is currently open, user include xsj, x64, linux, cnu, asm, and inside this you'll have a file unit unistd_32.h, and if you open with text editor, you'll see the hell lot of codes here. So what is this? This is the system call numbers. So like you want to write hello world on the console, so we have to generate a write call, like a cout in the cout statement in your C++ or a printf in C. So the first thing that we have to do is we have to provide the write call number to ex. Ex, I already told, ex contains the information related to the system call. So it will have which system call is it has to execute. So like if we see like it's a 0x4, so you can also write 4. That's nothing. That's no, that will make no difference, because like till 10, like 9, both the like hexadecimal and decimal notation are same. Now once you go after 9, the decimal value will change. So this is 0x4. Now what this is, so like for a write, so I can quickly show you the man page of write. Okay. Okay. So this is the man page of write, the second page. So you can see like every write call has 3 arguments: the buff, the count, and the ft. So the ft, I don't remember like what the full form is, but okay, it's file descriptor. So ft is the file descriptor. So like if you are writing something, you are reading something, so if it's a standard input, it's a standard output, it's a standard error. So like that's what is called a file descriptor. So 0 is denoted to file input, 1 is for file output, and 2 is for file error. So we are writing something, so that will be a standard output, so that will be 1, right? So we'll input 1 here. Now the second part is a buffer. So that this buffer means the actual message that we will output. So now that is another interesting part. So what we will do now, so there comes your data section. All the initialized data will be there in the data section. So here it is. So this is your data section. Oh lord, why I'm making these mistakes. Okay, so this is your data section. So what will be, so like if we write hello world, so what will be, it's like output, not output, it will like any variable name that you want. If you try to write example, you can write example, anything, any variable name that you want. This is the data type. So this I'll explain you in a later part of the lesson. For now, just remember this is like a data pipe and hello world. Now what we have will move is like the second argument will move this variable, the example variable. And what is the size? This size is 11. So I'll input 0 and input 11. Okay. Now, till now we have written a program, but now here comes the interesting part. So here, what this instruction I am writing, this is what, this is the interrupt that we are generating. So like for any like function call, any write function, read function, anything, there has to be interrupt. Like you are like re-verifying it to the kernel, like yeah, the instructions are correct, you have to execute it. So that part is called the interrupt to be generated. So till now we have we have written the program, but we have not closed it. So what we have to do is like we have to close it. So what is the exit code? It's 1. So we'll move EAX with 0x1 and we'll generate a interrupt. So I feel now we are good. So like what just give 1 second. There is space right here. Example dot nasm and we'll save it. So now we are having our first assembly language code. Now nasm is the compiler will compile that code. So I'm already having that compiler installed. If you are not having, you'll simply have to have that get install and nasm. That's it. So it's saying like it's already installed because I've already done it. So now we have to set the flavor. It will ELF 32-bit if I say. What will the output? It will be example.o. And what will the input? It will be example.nasm. And I click it, it shows instruction expected. What the error is, man? Okay, then line 13 it shows instruction expected error. Hey, this space might be creating the issue. No. Okay, so this we have written a mocks. This is remove instruction. Why do I make these silly mistakes, man? So now we are having the example.o file. So now I'll quickly open that. Here we already have. I'll be sharing the PPT with you guys. So this is already there. App.get on NAS. Oh. Okay, you're having this. This is what I did. Now I'll do the what will be the output. Output will just example. Okay, and the input will be example.o. Why do I make these mistakes? Okay, so it's done, I guess. Okay, so my bad. So I'm having a 64-bit OS and I'm generating a 32-bit. So I'll generate a 64-bit. And now I'll click output. So we'll have the example.exe. I'll quickly run the example.exe and here it is. Hello world. We are getting the hello world code that we have written. So thank you guys. That's it for assembly language, the beginning course. I'll come up with the advanced lesson of assembly language as well, where we'll be looking at the advanced part of assembly language, difference between 32-bit registers, 64-bit registers. We'll be actually disassembling a malware sort code, and then we're looking at its assembly language. So how the actual assembly language code looks like in real world. So that's it for today.